A time response of first order system for unit step response we will see in this class. So, this is the diagram, block diagram of first order system having the open loop gain as 1 by 1 ST and having unity feedback. So, H is equal to 1 here. The transfer function of this diagram can be given as g of s by 1 plus g of s into h of s. So, g of s is 1 by st and 1 plus g of s into h of s is 1. So, therefore, this is 1 by 1 plus s into t. As the denominator polynomial is having the power s power of n as 1. So, therefore, this is called a first order system. As the value of n is equal to 1, this can be called as first order system. So, the response, the time response of this first order system for unit step input will be shown as R of s is equal to 1 by s. So, therefore, the transfer function is C of s by R of s, Laplace transform of output by Laplace transform of input, which is equal to 1 by 1 plus st. So, to get the output, the response of the transfer function C of s is equal to R of s into the transfer function. So, R of s is unit step input. So, therefore, the Laplace transform of unit step input is 1 by s into 1 by 1 plus st. So, here this can be written as 1 by s into 1 plus st, and we are representing the denominator and numerator polynomials in terms of s plus p1 and s plus p2 like that in the denominator, and in the numerator we will be representing like s plus z1 into s plus z2, so on. So, by writing that one, the above denominator, so we are taking t as common here, so that this will be turning up into s plus something, s plus p1 form. So, here I am taking this t to the numerator here. So, therefore, this is 1 by t divided by s into s plus 1 by t. So, I can do the partial fractions for this, so that this can be a by s plus b by s plus 1 by t. To find out the a and b values, so this is the procedure to calculate the partial fraction constants. So, 1 by t divided by s plus 1 by t, where s is equal to 0, then you will get the value of a as 1. Similarly, for getting b, 1 by t divided by s, where s is equal to minus 1 by t, we will be having the value of b as minus 1. So, substitute these values and we will be getting C of s is equal to 1 by s minus 1 by s plus 1 by t. As b is equal to minus 1 here, I am taking sign here. I wanted to get time response of this first order system. So, therefore, to get the time response, I have to get in terms of t. So, therefore, I am doing inverse Laplace of this output. Laplace inverse of C of s is equal to Laplace inverse of this entire term. So, we know that 1 by s is nothing but 1, and the inverse Laplace of 1 by s plus 1 by t is e power of minus t by tau. So, this is the time response of first order system, which is consisting of transient response and as well as steady state response of the system. So, this is the steady state response, and this is the exponential decaying term is nothing but transient response of the system. If I take the values of time constants t, so generally we will be having the transient response of 5 time constants theoretically. So, we have to calculate for 5 time constants, substitute t is equal to 1 time constant in the above expression. Therefore, we will be getting C of t is equal to 1 minus e power of minus 1. So, therefore, this will be 0.632. So, 63% of the output will be obtained as an output. So, at a time 2 constants, we will be getting 0.865 times of the output. So, 86% of output will be obtained, and similarly at 3 time constants 0.95. So, at the end, at the final state, by applying t is equal to infinity, so we will be having a unit output. That means, the step input will be 1, having unit step input, the magnitude is 1. So, at the infinity time, so after reaching to steady state, it may be getting the output as also equal to 1. So, in practical there may be small deviation between input and obtained outputs. So, that deviation is called error, that is shown in this above figure. So, this is a time response of first order system for unit step input. Now, we will see second order system. Second order system. So, this is the second order system having the transfer function, open loop transfer function as omega n square by s square plus 2 zeta omega n into s, and having the unity feedback system h is equal to 1. So, therefore, the transfer function can be given as C of s by R of s, which can be written as omega n square divided by s square plus 2 zeta omega n into s plus omega n square. So, this is the closed loop transfer function of second order system, where omega n is the undamped natural frequency, undamped natural frequency in radians per second, and zeta is the damping ratio. Zeta is the damping ratio. It can be defined as, it is a ratio of actual damping to the critical damping. Actual damping to the critical damping is called the damping ratio. Actual damping to the critical damping is called zeta, damping ratio. So, depending upon this zeta, so we are having 4 cases. For example, if zeta is equal to 0, then this system can be called as undamped system. Undamped system. If zeta is less than 1 and greater than 0, this can be called as underdamped system. Underdamped system. Zeta is equal to 1, this can be called as critical damping system. Critically damped system. If zeta is greater than 1, then this can be called as over damping system. The characteristic equation of the second order system can be written as, so the denominator of this transfer function, characteristic equation is s square plus 2 zeta omega n into s plus omega n square is equal to 0. So, the roots of this equation can be written as S1 and S2, which is equal to minus b plus or minus under root of b square minus 4ac by 2a. So, this will be 4 zeta square omega n square minus 4 omega n square divided by 2a. So, this can be further simplified as minus 2 zeta omega n plus or minus under root of, I am taking 4 omega n square as common. So, this will become now zeta square minus 1 divided by 2. So, if I remove this 4 omega n square from the root, then S1 and S2 will be now minus zeta into omega n plus or minus omega n into root of zeta square minus 1. So, this is the simplified roots of this characteristic equation S1 and S2. So, case number 1, when zeta is equal to 0, so the roots will be now, substitute zeta is equal to 0 in this roots. So, here the S1 and S2 will be plus or minus j omega n. That means roots are purely imaginary. Roots are purely imaginary, and the system is called undamped system, and the system is undamped system as zeta is equal to 0. And in second case, if zeta is equal to 1, then the roots S1 and S2 will be minus omega n. That means roots are equal and real. Roots are real and equal, and the system is critically damped system. System is critically damped system. Similarly, if the zeta value is more than 1, if zeta is greater than 1, then the roots will be S1 and S2, which are minus zeta omega n plus or minus under root of plus or minus omega n into under root of zeta square minus 1. So, here the roots are real but not equal. Roots are real and unequal, and the system is over damped system. Over damped system. Next one, if zeta is lying between 0 and 1, then the roots S1 and S2 are minus zeta omega n plus or minus omega n into root of zeta square minus 1. So, here if I take minus 1 as common, therefore, minus zeta omega n plus or minus omega n, if I take minus 1 as common, then this will be 1 minus zeta square. So, here zeta into omega n plus or minus omega n into root of minus 1 into root of 1 minus zeta square. So, this will become now zeta into omega n plus or minus root 1 is nothing but j omega n into root of 1 minus zeta square. So, this I can write like zeta into omega n plus or minus j into omega d, where omega d is the damped frequency of oscillations. Damped frequency of oscillations. Damped frequency of oscillations of the system, where omega d can be written as omega n into root of 1 minus zeta square. So, this is the damped frequency of oscillations, and so the roots are here minus zeta omega n plus or minus j omega d. Roots are complex conjugate and the system is under damped system. So, here roots are complex conjugate to each other, complex conjugate to each other, and the system is under damped system. Under damped system.